Okay, think about like Iron Man taking off, right? Or maybe one of those huge sci-fi ships.
Yeah, massive thrusters, maybe a launch pad, or just that sort of stable, symmetrical hover like a drone or a helicopter.
Exactly. But then you watch a goose or like a falcon,
hmm
they just pop straight up off the ground. Looks totally effortless, no runway needed.
And that difference, that huge gap between how our machines fly and how, well, a bird actually flies,
Yeah.
is a massive challenge in robotics.
We've kind of nailed insect flight, haven't we? That tiny, buzzy, symmetrical flapping.
Yeah, and obviously fixed-wing flight like airplanes, but that versatile, low-speed takeoff birds and bats use, where they launch themselves, that's been much harder to crack.
Right. So how do you build a robot that can do that tricky asymmetrical launch without it being, too heavy or way too complex to actually control?
Well, that's what we're digging into today. We're looking at a paper that claims they've actually done it.
Oh, interesting.
Yeah, our mission here is to unpack the creation of this new robot. They call it RoboFalcon 2.0. And it seems to successfully mimic that bird-style self-takeoff.
RoboFalcon 2.0. Okay, I'm hooked. Where's this research coming from?
Okay, so the paper is titled, Flapping Wing Robot Achieves Bird-Style Self-Takeoff by Adopting Reconfigurable Mechanisms. It was published in Science Advances.
Science Advances. Okay.
And the work comes mainly from Northwestern Polytechnical University in Xi'an, China. The authors are Ang Chen, Bifeng Song, Kang Liu, Jie Wang, Dong Xu, and Hongdui Qi.
Got it.
And the absolute key, the core idea they managed to replicate, is this really specific wing motion called flap, sweep, fold, FSF for short.
Flap, sweep, fold. FSF. Okay. Sounds kind of simple when you say it like that.
Deceptively simple, maybe.
Right. But this FSF motion, you're saying that's like the secret sauce for slow flight in vertebrates, not just takeoff.
That's exactly right. Birds, bats,
Right.
they use this for takeoff, for landing, even for hovering in some cases. It's sometimes called asymmetrical hovering or slow flight.
Asymmetrical. How's that different from, say, an insect?
Well, think about a bee or a fly. Their wings generate lift on both the downstroke and the upstroke, moving back and forth pretty symmetrically.
Okay.
But a bird, especially a larger one taking off,
Mm-hmm.
relies almost entirely on that powerful downward stroke. The upstroke is different.
So break down the FSF for us. Flap, sweep, fold. What's happening?
Okay, so it's this really neat coupled motion. During the downstroke, this is the power stroke, the wings are fully extended, big surface area.
Max power.
Exactly. They flap downwards, that's the flap part, or ventral flapping. But crucially, they also sweep forward at the same time, anterior sweeping, that's the sweep.
Down and forward.
Yep, that's the only part that's really generating this significant aerodynamic force, the lift and thrust.
Got it. So what about the upstroke then? And the fold?
Right, the return stroke. This is where the fold comes in. To avoid fighting against the air on the way up, the wings quickly flex or fold or tuck in close to the body.
Makes sense. Less drag.
Precisely. Tucking reduces the wing area, makes the upstroke aerodynamically pretty much inactive. It saves a lot of energy.
Okay, so this whole down and forward power stroke tucked up recovery.
Yeah.
Why is that specific geometry so vital for takeoff?
It naturally creates this forward-leaning stroke plane. If you picture a hummingbird again, its wing stroke is mostly horizontal, right?
Yeah, buzzing back and forth.
But this FSF motion is tilted forward. That inclination is super important because it lets the bird push a huge amount of air downwards. And that's really the only way to support its body weight when it has zero forward speed, like right at liftoff.
Needs that downward thrust immediately.
Exactly. And the paper points out you see this everywhere in nature. Mallards taking off, turkey vultures, Canada geese, even bats landing slowly, or a kingfisher hovering. It's nature's go-to solution for launching at low speeds.
Okay, so the biology makes sense. Flap, sweep, fold. Cool. But building that into a machine, a robot falcon, you said.
Yeah, RoboFalcon 2.0. It's not small either. About a 1.2-meter wingspan, weighs almost 800 grams, so medium-sized bird scale.
Right, and translating that complex FSF dance into that kind of hardware, that sounds like a serious engineering challenge.
Oh, absolutely. It's the classic problem in this field, what you might call the complexity contradiction.
Meaning?
Meaning, to get that FSF motion, you need the wing to move in 3 different ways, right? Flapping, sweeping, folding. 3 degrees of freedom.
Okay.
Now, the obvious engineering approach might be, okay, let's put a motor on each movement. But you need powerful motors for flapping, especially on an 800-gram robot.
Right. Motors mean weight, and batteries mean weight.
Exactly. So if you add 3 powerful motors, plus the batteries to run them, plus the complex controls,
Yeah.
suddenly your robot Falcon is way too heavy to even lift itself off the ground. It's catch-22.
So you need the complex motion, but you need to achieve it with, like, mechanical simplicity to keep the weight down. How did this team at Northwestern Polytechnical University solve that puzzle? Did they, like, cheat physics?
Huh? Not quite cheat physics, but they're very clever mechanically. They developed something they call reconfigurable mechanisms, sometimes called decouplers.
Reconfigurable mechanisms. Decouplers. What are those?
So instead of multiple big heavy motors, they use just one primary high-power motor, a brushless DC motor, a BLDC. That provides the main flapping power.
Okay, one main engine.
Right. And then these reconfigurable mechanisms, these decouplers, are essentially smart linkages and gears. They take the single powerful rotation from that main motor and cleverly convert it into the 3 different coordinated FSF motions.
Ah, I see. So the power comes from one place, but these lighter mechanisms guide the wing through the complex flap, sweep, and fold pattern.
Precisely. The big motor does the heavy lifting, the flapping, via something called a conical rocker mechanism, or CRM. Other mechanisms handle the folding for the upstroke.
But which part was the real breakthrough for takeoff control?
That seems to be the sweeping decoupler. This is the key innovation. It uses a tiny, lightweight servo motor, not for power, but for control.
A servo, just for adjustment.
Exactly. This servo adjusts how much the wing sweeps forward during that downstroke. It can change the sweep angle from just 5 degrees, almost nothing, up to a much more significant 25 degrees.
And that small adjustment angle controls the takeoff. How?
Because it fine-tunes that FSF pattern. More forward sweep on the downstroke, more backward sweep on the upstroke, and crucially, being able to vary that sweep amplitude gives the robot its main control knob during that difficult low-speed launch phase.
Okay, so they can adjust the sweep. What does cranking up that sweep angle actually do aerodynamically? Did they test this?
Oh yeah, they did wind tunnel tests and also ran detailed computer simulations, computational fluid dynamics, CFD, to really see what was happening with the airflow. They looked at different conditions, takeoff in still air, slow flight, slightly faster flight.
And what did they find? What's the payoff for more sweep?
2 really big things, especially when the wings are flapping fast like they need to for takeoff. First, increasing the sweep significantly boosts the lift.
More lift. Good for takeoff. Makes sense.
Yep. And second, maybe even more critically for control, it creates a much stronger pitching moment.
Pitching moment. That's the force that makes the nose go up or down, right?
Exactly. In this case, more sweep means a much stronger nose-up pitching moment.
Okay, more lift and a strong nose-up tendency. Sounds perfect for jumping off the ground. But why? What's the physics behind why sweeping forward does that?
This is where the CFD results were really cool, kind of the wow moment in the paper.
Lay it on me.
Okay, so that dynamic forward sweep during the power stroke does something amazing to the airflow over the wing. It enhances something called the leading edge vortex, or LEV.
Leading edge vortex, LEV. What's that? Like a little whirlpool?
Sort of. Think of it like a stable swirl of low-pressure air that forms right along the front edge of the wing as it moves. Delta wing jets use LEVs for lift, too.
So the wing isn't just pushing air down, it's also creating this low-pressure zone on top that essentially sucks the wing upwards.
You got it. The forward sweep makes that LEV stronger and more stable, giving a significant lift boost.
Okay, that explains the extra lift. What about the nose-up pitch?
That's the second effect. When the wing sweeps forward during the downstroke, more of the wing's area is physically positioned ahead of the robot's center of gravity, its CG.
Ah, okay. So the lift force is being generated further forward relative to the balance point.
Precisely. This effectively shifts the overall center of pressure, CP, where the aerodynamic forces act further forward.
And if the lift acts further forward from the CG, that creates more leverage, right? Like pushing a door further from its hinges.
Exactly. It prolongs the rotating arm, as the paper puts it, that significantly increases the nose-up pitching moment.
Wow. Okay, so sweep gives you lift and pitch control bundled together.
And that's incredibly useful for takeoff.
Yeah.
At very low speeds, normal control surfaces like a tail elevator are basically useless. There's just not enough airflow over them.
Right.
So here, the wing sweep itself becomes the primary way to control the robot's pitch angle during that critical launch phase.
That seems really elegant, but also maybe a bit tricky. If sweep controls both lift and pitch, can you control them independently? What happens when you start flying faster? Doesn't that nose-up force become a problem?
You've hit on the exact challenge they encountered. It is tricky. They saw this first in their computer simulations. They used a physics simulator called MuJoCo.
MuJoCo, okay.
And the simulation showed the robot, starting tilted up at 45 degrees, could use that sweep control to lift off, stabilize its attitude, and start to level out.
But there's always a but.
But just like you suspected, as the simulated robot picked up speed, getting past maybe 3 or 4 meters per second, that powerful nose-up pitching moment from the sweep just became overwhelming. The pitch angle started going haywire, diverging upward.
Couldn't keep the nose down.
Exactly. The control system couldn't fight it. And this simulation result led directly to a necessary tweak when they built the real thing, the RoboFalcon 2.0 prototype.
So the real robot had the same problem.
Pretty much. They did tethered flight tests safety first. And yes, it took off beautifully using maximum sweep, just like a bird. Really impressive.
Cool.
But also, just like the simulation, once it accelerated a bit, it struggled to maintain pitch control. That nose-up moment was too strong.
So how did they fix it in the real world? Did they add a tail?
Nope, not a tail. They went for a simpler, maybe slightly less elegant, but effective fix. They adjusted the robot's balance.
How? Added weights.
They shifted the center of gravity, the CG, further forward.
Yeah.
Specifically, they mounted the battery not inside the main body, but out front on an extended carbon fiber rod.
Ah, putting the battery on a stick out front. That sounds a bit like a cheat. Or just practical engineering.
Huh. I'd lean towards practical engineering, maybe inspired by biology. Birds and bats subtly shift their posture and body mass distribution all the time during flight maneuvers.
Okay, fair enough. So moving the CG forward helped.
It did. By having the weight further forward, it provided passive stability against that strong pitch-up tendency from the wing sweep. With the offset CG, the RoboFalcon could accelerate up to 6 meters per second while keeping a stable lower pitch angle.
So they achieved a controlled bird-style takeoff, even if they needed that battery stick.
They did. It's a really significant demonstration of this kind of takeoff locomotion in a robot of this scale.
It sounds incredibly complex to get right. But what about efficiency? You mentioned those tiny insect bots earlier. How does RoboFalcon stack up energy-wise?
Yeah, that's an important point the researchers acknowledge. While RoboFalcon 2.0 achieves this amazing biomimicry and maneuverability, it's not built for efficiency right now.
Power hungry.
Relatively speaking, yes. Especially compared to smaller flapping robots that often use resonance, kind of like tuning fork physics, to flap very efficiently with less power. This RoboFalcon is more about proving the complex flight mechanics are possible, not necessarily about winning any endurance awards yet.
Okay, let's wrap this up. If you're listening, here are maybe 3 big takeaways from this deep dive. First, the biomimicry mastered part.
Right, that flap, sweep, fold motion, the FSF. They successfully translated it from birds to a working robot. It really replicates how vertebrates take off at low speed.
Second takeaway, reconfigurable simplicity. This is the engineering magic.
Yeah, using those smart decoupler mechanisms let them get 3 complex wing motions, flapping, sweeping, folding, all synchronized from just one main power motor. That solved the weight versus complexity problem.
Okay, and the third one, a new low-speed control strategy.
Absolutely. Adjusting that wing sweep angle proved to be a really effective way to control both lift and pitch right when you need it most during that low-speed takeoff. When normal control surfaces wouldn't work well, the wing itself becomes the control.
So this work really opens a door for building larger, more bird-like robots that can launch themselves. But looking ahead, what's next?
Well, the paper suggests the bigger picture is extending the flight capabilities. To go from this specialized takeoff to, say, fast, efficient cruising flight, future versions will likely need more complexity.
Like what?
Maybe adding an active tail for better high-speed control, or perhaps developing a system that can shift the robot's center of gravity automatically on the fly, instead of just having the battery fixed on a stick. More dynamic adaptation.
Mimicking biology even more closely.
Exactly. Which leads to kind of a final thought for you, the listener, to chew on.
Hit me.
If it took this much mechanical ingenuity, these decouplers, the careful tuning, the CG shift, just to get one specific flight phase, the FSF takeoff, working in a robot, just think about a real bird. Think about the millions of years of evolution packed into its muscles, bones, feathers, and nervous system. What incredible unseen complexity allows that bird to switch seamlessly from that high-power, low-speed FSF launch straight into high-speed, efficient cruising, and then back again for landing, without missing a beat. What are we still missing?